record. So okay.
Study.
All right. So at this time, we're gonna go ahead and get started. Today's lesson. So I need everybody's full attention. A couple of announcements before we get started. First up, we are halfway done with the unit. There are 6 lessons. So after today, we'll be 2/3 done with the unit. So that means you have a test coming soon in a couple of weeks. I'll give you the exact day once next week passes. But next class period is going to be a little bit strange on Tuesday because you can't be in this classroom on Tuesday because that is the chemistry lab retake exam day. The good news is that lab retake is after lunch. So I will have it set up once I put you all out after tutoring on Monday. I will be setting up after school and I'll have it set up for Tuesday morning. So what we're going to do is I'm going to still be teaching just your class period. I won't be teaching my previous class that day, but I do want to move forward with your class period. So I will be teaching your class, but we're going to be traveling to Jedime's room. So we're going to be just going 2 classes down. And her classroom is actually set up pretty close to what this classroom setup is with the front. So I'll be setting up in there and teaching the lesson 5 in Jedime's room on Tuesday. So that means we'll be meeting at that door. You can still come here and then I'll bring you there, but you can't come in the room, basically. So if you wait outside the door, you won't be let in. There won't be anybody in here. Yes.
Does she have a first period?
She has a planning period in first period. So she will be lending us her classroom for first period. She'll probably be in there with us. She will also be administering the exam with me after lunch. So both her and my 3rd and 5th periods will be going to the media center most likely. But I wanted to teach my first because that's a tested class. And she wants to teach the first half of her 3rd because that's actually AS biology. Oh. So yes, she will be teaching her first half of AS biology on Tuesday after we leave the room. And then after lunch, she's shutting her stuff down as well. Basically, will be shut down for the lab exam. Because it's only a couple of students that are testing, I have the ability to be able to teach earlier in the day. I did last year too, actually. I taught, if you'll recall for the lab retake, I taught the first half of my 4th period. And then during lunch was when I ran and did the setup, like finished like any final preps of the setup. And then after lunch, you have to go to the media center with like an assignment to do if you were in 4th period, if you'll recall. So that is not unusual, but I just can't use this classroom that day. So we'll be going to Mr. Dimes. So that was the one thing that I wanted to get out of the way. So if you come in late on Tuesday and you knock on this door, where should you go? I'll put a sign on it, but you should go down to Jedime's room. So that was the one thing. This remote question.
How likely do you think the board will be updated during the lab exam?
I hope not. I hope that it will, roll up and not back down to 0.
I mean, at least won't be rolling back to 19.
Right. So, okay. So that's the one thing. The second is I had already mentioned your test is coming up in a couple of weeks. Expect it because there are 6 lessons in the unit. So after today, we're 2 lessons away from being done. I want to I'm trying to work out the review day right now for the test. We're either going to do a lab that day or like review activities or a combination of both. I'm thinking of doing an enthalpy of solution type lab because there are paper 3 labs where you have to calculate enthalpies of solution. So I'm going to look through like my old labs to see what there is available, but that won't be happening next week. That would be happening the week after. Will be when our review day is for the Unit 2 exam. All right, so today's lesson, Unit 2, Part 4. I apologize in advance. This lesson has some components in it that I think are confusing. I will do my best. I was looking over it. I was telling some people for like over an hour last night, making sure that I'm trying to be as clear as possible when explaining it. But I do understand that some of the stuff here can be confusing, especially in the last part of the lesson. Today, we're going to be going over something called enthalpy changes of solution, which is delta H sol. You're going to see a lot of delta H's in this class. So today we're gonna learn a few new delta H's. Delta H sol, delta H HYD, hydration, and then we're also gonna be combining that with the lattice enthalpy to find something called the enthalpy of solution. I don't remember, we may have done an enthalpy of solution lab last year. I know we did enthalpy of neutralization, but enthalpy of solution is basically the enthalpy change when you take an ionic compound and you dissolve it in water. That's what it is. And so we're going to learn how do you calculate this and what theoretically is going on. So beforehand, let's go ahead and go over the bell work because I think one person got 5 out of 5 on my check, but I don't remember if anybody else did. So I'm going to go over what the marks were here, how you would earn them. So these 3 were straight up from the lesson, pretty much. The first mark is to say, down the group, the thermal stability increases. So if you said, down the group, thermal stability increases, that was worth one of the 3 marks here because they told you to describe. They didn't tell you what the trend was. Whenever they're asking you for the trend, there's usually a mark associated with just the trend. So down the group, thermal stability increases. That's one of the 3 points. The other 2 points can be found directly in the notes from the lesson. I did go over them. One of them is that as we go down the group, the charge density decreases, or the ionic radius increases. You could say that. So down the group, ionic radius increases. Alternatively, you could have said charge density decreases. Same thing. And then the final mark is to say, so there will be less polarization of the anion. The less polarization of anion. Those were the marks you needed to hit for the points. The equation. A lot of you did get the equation correct. Yay. So this, you had to know that it's LiNO3. Lithium is a group 1 metal, not a group 2. So you would get Li2O plus NO2 plus O2, and then you have to balance it. And so I saw the way that most of you balanced it was you went 2, 2, and 1/2, but you could have also done 4, 2, 4, and 1. And that would also be the same thing. They accepted both answers. And so most people got this. You did not need the states of matter. They did not ask for it, but many people did get the states of matter accurately. Solid, solid, gas, gas. Sometimes you could be asked for states of matter, so you just have to look at the question. And then finally, suggest, this was the poorest scored question. And actually, it's one of the hardest objectives, types of command words. When they say suggest, what does that mean? That means that you might not have been directly taught this, right? Same thing with this. You were not directly taught how to do a thermal decomposition for a group 1 metal. You were only directly taught how to do it for a group 2. So they're asking you to basically connect some dots to come up with how you would come across that. So this is what they consider to be the hardest marks on a Cambridge exam. About 30 to 35% of the marks are those harder type of, you have to put a bunch of ideas together to come up with your answer. And that's how you get to those A-level scores, is you have to be able to suggest things that you haven't been directly taught. All right, so then the answer here. Well, lithium already has only a +1 charge, right? So what happens as I go down the group? The ionic radius gets larger and you have a really, really small charge. So the charge density would be decreasing. So the way that they explain the answer is the charge density of the other ions is so small it can't polarize the anion. So the group 1 ion is so small it cannot polarize the anion. Because the charge density, remember, for charge density, we're looking for the smaller and we're looking for the greater the numerical value. So if the numerical value is the same down the group of the ionic charge, it's the size that's making the difference. And when you have a large size and a small charge, it's not really going to be able to pull additional electrons toward it very well. Yes?
So I have a question.
Go ahead.
Why do when the ions become larger, why do they become more thermally stable?
Because you can't decompose them as easily, meaning that because this doesn't have the ability.
Good morning, please pardon this interruption.
It doesn't have the ability to
I
weaken the
apologize
bond.
for delay. At this time, students who need to test Algebra 1 retakes and the ELA retakes,
Omar is best.
or if you didn't test yesterday, please meet me in room 249. That's in the band hallway behind the red doors. Thank you. Please also make sure you are wearing your IDs around your neck. Thank you.
Okay, so Ramon, because I got interrupted when I was trying to explain. The idea is that this actually can't weaken the bond. So like, let's say that this was together with carbonate, just as an example. This doesn't have the power to pull this very strongly, which means that this oxygen doesn't get pulled off the carbonate because this doesn't have the power that something, for example, if it's smaller, then it has a greater ability to pull. And if it has a larger charge, then it has a greater ability to pull the electron clouds to it. And remember, the reaction itself is this breaking off and joining that element. The oxygen breaks off the carbonate and it joins the metal. So like here with the nitrate, you can see that it goes from NO3 to NO2 because one of the oxygens is joining with the lithium. That's the idea. So the lithium has to be small in order for that to happen because it already has a small ionic charge. So if it has a large size, like small ionic charge, it's really not going to be able to pull towards it. That's the concept. Yes.
So that's a good tool. Like that means like it makes it help like more stable.
If it's able to pull the oxygen off, it's less thermally stable.
And then
If it's not able to pull the oxygen off, then it's more thermally stable because the reaction's not happening. That's the idea. All right, good questions. And you can see why we spent one day kind of just on that one standard, because it is one of the trickier ones to be able to wrap our minds around. Unfortunately, today is also one of the trickier concepts to wrap our minds around. Yes. Yeah, go ahead. So these are our objectives. Yes, there are more than one because we have to get through some explanations to see what's going on. Define and use the term enthalpy change with reference to specifically the concepts of hydration. When you think of hydration, what do you think of? Water. So water is going to be involved here. And solution. So those are the two enthalpy changes, new enthalpy changes we're going to be learning today. This one, we're going to see it as delta H high. And this one, we're going to see it as delta H cold. So just like we had all the K's last unit, we have all the delta H's last unit. I remember last year somebody saying, I'm scared of triangles on their like initial like survey on the first day of A-level chemistry. They said, I'm scared of triangles. And I responded, I'm so sorry because of all the triangles that are here. All the enthalpy changes. This unit is all the triangles, all the enthalpy changes. All right, so then constructing using energy cycle. Remember this thing? Remember this thing? No! We're doing this today. No. Bye.
I needed
We did that in enthalpy.
It's not even, is that not even the full, like, new one?
Yes.
It's suicide prevention one. Let me just say that.
That's great.
I mean, you could come up with a formula without the cycle to make life a little bit easier. There is a way to come up with a formula without the cycle, but it does say construct an energy cycle. So there is a non-zero chance that on your paper 4 specifically, you could be asked to construct an energy cycle involving these enthalpy changes. How many marks is that enthalpy cycle worth? You can check. It's forward in the lesson.
2, 3.
It's right.
3-1. 3-1.
2 out of 100.
It's not that bad. The cool one. God damn it. Isn't the cool one?
Okay, non-zero chance, but has it happened before? Like, have
We can take a look. I can analyze that when we get closer. I have to like count them all up. No. Carry out calculations. That means use a formula I'm going to give you or create a cycle, your choice. I am going to give you a formula. I prefer using the formula myself. because these make my brain hurt too. To be fair with you, when I studied all my chemistry classes in America, I never saw this in my life. The first time I ever saw this was when I was teaching Cambridge, and I was like, why do they do it like this? So we have a different way in America of approaching Hess's law, but this is the way that the Cambridge International has you approach Hess's law. All right, carry calculations involving the energy cycle. Explain in qualitative terms the effect of ionic charge and ionic radius on the enthalpy change of hydration. So guess what? That sounds to me like charge density is back in play again. That concept of charge density, which was in the last lesson, which was in the first lesson, which is in the second lesson, is all over the place in terms of how you explain your answers. So I think there's actually more standards here that I forgot to add in. So I will take a look and I'll add them to the next lesson just so you know what they were. They're going to be the explanation of the solubility of sulfates and hydroxides. We're going to be explaining, so I'll give the exact number to you, but we have to explain the trend of solubility. So you want to add this in of sulfates and hydroxides. Do you remember the trends from last year?
No, I always forgot.
I remember they were opposite.
Yes,
Yeah,
they
that's
are
the only-
opposite.
that's the only-
Down the group for sulfates is bad.
Sulfates, down the group,
It's barium sulfate.
decrease.
No soluble.
Hydroxide, down the group, increase. So today we're gonna learn why they're opposite to each other, why the solubility of sulfates decreases down the group, and why the solubility of hydroxides increases down the group. Or we're gonna make our best attempt at learning that because it's a 4-mark explanation if it shows up on the Cambridge exam.
We didn't already know it?
What?
We didn't already know it?
You knew the trend, you don't know why? Or do you know why? You explain why?
I did not know. I thought.
It has to do with the changes in lattice enthalpy and enthalpy of hydration and how that affects the enthalpy of solution.
Of course.
So I haven't explained it what any of that is really yet. So that's the last thing we're gonna get to in today's lesson. So try to focus as best as you can. I am recording the lesson so you can go back over it as needed. I also suggest, I think it's only a page in the textbook, but I also suggest reading it in the textbook if you need to. I also posted a video this morning I was looking over. From the organic chemistry tutor. I don't know if you've ever seen any of their videos before. But I posted that as a resource on Google Classroom just in case you wanted to see it explained from a different person. The enthalpy of solution, lattice enthalpy, hydration enthalpies, and what all that means. But here we go. So starting into the notes, enthalpy changes of solution. What are we talking about here? So looking at the standard, it says we have to define it, right? Which means, what does it mean when it says define? Word for word definition. That's a flashcard. If you want that mark on a test, it's a word for word definition. So the enthalpy change solution is defined as energy absorbed or released. That means if I gave you a question where you had to check mark, is it always endothermic, always exothermic, or could be either? The answer is could be either, right? So it's the energy absorbed or released when a mole of an ionic compound dissolves in sufficient water, so excess water, to make a very dilute solution. And yes, you do have to get the word dilute solution in there. And so this is a image I found of what's happening at the particle level, I want to say, of what's going on. This is sodium chloride, so Na plus, Cl minus. This right here is what we call the ionic lattice. You remember that word?
Yes.
Ionic lattice, all the negatives and positives, negative, positive, negative, positive, negative, positive. So when I take sodium chloride and I put it in water, why does it dissolve? Why does it dissolve? But other ionic compounds have charges and they don't dissolve. AgCl has a charge, it don't dissolve. Why does it dissolve?
Got me there.
What's the general concept of what happens when it dissolves? Let's start with that.
It breaks down.
So how is it able to break apart? Because it wants to be together, right? water's polar, so what's happening with the water molecules as you stir it? Ramon?
The what's it called? The little like IMF, I guess.
Yes.
Intermolecular
The
forces?
IMF, the intermolecular forces. Basically, what's happening as you stir it is the water molecules are starting to kind of grab these ions off of the lattice. But in order for that to happen, you have to have a very large amount of water to make that happen. So you need enough water so that the water molecules are able to grab the substance you're trying to dissolve. And this is how solubility of solutions work in general. Now, what makes one soluble and one not soluble? We'll look at all those factors shortly. But this is the general concept of what's happening. You have to break, basically, you have to break these bonds, right? You have to break the bonds of the ionic lattice. Would you agree? Like this has to break apart, and then new bonds form between the water and the ions. These new bonds form here. And these are bonds forming. You may want to write that. Bonds forming. And these are bonds that have to be broken. Wait, if bonds are broken and bonds are forming, isn't that endothermic? And for bonds broken, that's endothermic, and bonds forming, that's exothermic. So are we talking about energy changes here? That's exactly what today's lesson is about, is what are the energy changes associated with breaking this apart, and what are the energies associated with putting these together. So just to give you an idea of what we're discussing today, that's the main idea. In order to understand this, first, we have to discuss what are the equations for enthalpy of solution. So what would you be asked to write down if you were asked to describe an enthalpy of solution? Yes, Ansel.
So if this precipitate, it's just like pure sodium, right?
There's no precipitate.
Oh, right.
No, there's no precipitate. If there were excess NaCl at the bottom, we don't call it a precipitate, it's just called excess solid at the bottom. A precipitate only forms. A PPT is defined as a solid forming after mixing two aqueous solutions together. So you don't start with a solid, but when you mix the two aqueous solutions together, you end with a solid. That's what the definition of a precipitate is. So mixing two aqueous solutions together. And I think that might get us in a little bit of trouble on paper 3, which thankfully we've already passed in the qualitative analysis. Because in that paper 3, if you were to make a precipitate, you can only call it a precipitate if it wasn't a solid to begin with. If you started with a solid, and then you call it a precipitate, it doesn't make sense.
If you add a copper silver nitrate with the silver
You can say the silver is precipitated, but there's also the color change that you would discuss. You would have to say white solid formed, or was that silver?
silver solid form.
Silver solid formed, yes.
So like the hydrogen with the positive charge is bonding to chlorine, negative charge.
So the partially positive hydrogen from the water is bonding to the negative chlorine in a specific type of bond I'm about to teach you shortly.
So
This is just a general idea of what's going on, yes.
also then what happens with the sodium? Like it
The
should bond,
sodium here,
yeah, it should bond with the
it
oxygen.
goes to the negative oxygens of the water.
Why doesn't that leave a precipitate or something?
If you have enough water, the water takes off the salt and dissolves it. That's why it says sufficient water. So to dissolve it all, you need sufficient water to make it happen. If you don't have enough water, there would be still some solid at the bottom, but we don't define that as precipitate because it's not something new that's made. It was always there. As I said, that could have got us in a little bit of trouble on paper 3, which has already passed. But just so you're aware, you should know that a precipitate is only formed from two aqueous solutions. Otherwise, you just call it excess solid at the bottom. All right, so what is the equation? This is the type of equation you're going to see for enthalpy of solution. You take a solid ionic compound and you put plus AQ. Could you put plus H2O instead? I mean, technically, but if you do, you may want to try to balance it and do a double replacement reaction. And that's not what you're showing. You're just showing what happens when I put the solid in water. It's another way of looking at the dissociation. And it's just saying, okay, it dissolved. It becomes aqueous without showing the ions. So what would have been equivalent to this is MgCl2. And then if we write, I would have written it like that, throw it in water, but this is not how Cambridge writes it. Cambridge writes it like this. And then you could also say this. This is the same thing. Can't spell, but that's supposed to say. Anyways. Thank you. Same idea. Solid, you throw it in water, you get their ions dissolved in water. That's the same thing this is saying right here. What does this sign mean? Delta H sol, negative.
Energy is released.
Energy is released through this process. How would that be observed? And as I said, I'm leaning towards having us do a lab with this for this reason. How would that be observed?
Temperature go up.
Temperature go up in thermometer, right? Exothermic temperature and thermometer will go up. You would do this in a little foam cup. It would be like that. You'd have a thermometer. And then as the energy is released, you'd see the temperature increase. And that tells you, yes, this is an exothermic reaction. And then what about NaCl? Same idea. What's happening here with this delta H sol? A little bit of energy is absorbed. A slight amount of energy is absorbed in this, meaning it actually takes a little extra input of energy to get salt to dissolve in water. Which to me makes sense, because I know for certain that I have to stir it pretty well to get it to dissolve. That means that magnesium chloride takes a lot less energy. It gives more energy out, so that means it's going to dissolve easier. Yes.
Does that mean that there's compounds that it's better to not stir for them to dissolve?
Not better to not stir, but they just dissolve faster. I would say hydrates, for example, dissolve very fast for the most part, unless it's copper sulfate. Yes.
So does that mean if you have like boiling water, if you add enough of a salt, you can cool it down?
If you add boiling water,
If you have boiling water,
Oh,
you
yeah.
add enough of the salts, can you like cool it down then?
what do you mean by cool it down?
It's like
As in like,
Oh, like cool down the water?
Yeah.
Yes.
It also changed the boiling point a little.
Yes, it does change the boiling point, which is a topic that needs to go into the Olympiad review sessions because it's not in here. But boiling point elevation and freezing point lowering is something called a colligative property, and salts do have that effect on water. All right, Yes.
Like when it says energy release, I mean,
we should add that to the review for this unit because it's semi-related. Yes.
it's like forming more bonds.
What do you mean?
Like when it's negative, that forming more bonds, or like.
It means yes, most likely. Yes, you can assume that that could be a possibility happening. All right, so then AQ by Cambridge is defined to mean that we have sufficient water for this dissolving to take place. So whenever you see AQ, it means you have enough to dissolve it. Enthalpy changes of solution can be endothermic or exothermic. However, you can actually predict solubility based on your enthalpy of solution. The more negative it is, the more soluble your salt is. The more positive it is, the less soluble your salt is. And so eventually you get to a point where the delta H sol is largely positive and you're not really going to be dissolving much of your ionic salt because you need to put in too much energy for it to happen. It doesn't give you an energy payoff. And so we say instead of insoluble, we use the word sparingly soluble, and you'll see that later on in the lesson if we have something with a large delta H sol. All right, so what is the equations that they want us to write? Write equations to represent the enthalpy change of solution. How does that look from Cambridge? First of all, do you have to know how to put potassium sulfate together?
Yep.
So what would that be?
That's gonna be K2SO4.
K2SO4 is absolutely correct. Because we know sulfate has a -2 charge and potassium has a +1. And that's how they crisscross. And then what do I have to do?
We're gonna put it in solid state.
And then plus AQ. This is how Cambridge wants us to write it. And then K2SO4, you do not need to show the ions spread apart. like with the plus charge and the minus charge, they say if you just write that it's dissolved in water, that's good enough. Although I can't imagine they would count it wrong if you did break it apart into the ion. That's what I would naturally want to do, and it's not incorrect to do that, but this is how it would show the responses. So if you did 2K plus AQ plus SO4 minus 2 AQ, that should be okay. Zinc chloride. CnCl2. State of matter to start. Solid plus AQ becomes CnCl2 AQ. And so this equation right here is the enthalpy of solution. All this describes to us is a solid. We throw it in water, it dissolves. Enthalpy of solution. Question from the textbook. Can you predict the relative solubilities of these four compounds based on their enthalpies of solution? What would be the most soluble to the least soluble? So let's go most soluble to least soluble in that order. What would be the most soluble salt here?
Sodium bromide.
Sodium bromide. So NaBr is going to be the most soluble. So what comes after that?
Sodium chloride.
Sodium chloride. What comes after that?
So
So we got this, then silver chloride. Then what? Silver bromide last, which makes sense because these always come out as PPTs, right? If we were to mix two things together, if we got a white PPT from it, if it was silver that we added, we can assume that we have a chloride and then it's AgCl, and if it's a green PPT, it's AgBr. So that's in line with what we already do now. That these are going to dissolve in water quite easily because they come from a group 1 metal. And silver compounds with chloride, bromide, and iodide don't really break apart. They form precipitates. All right, so just a note here. All ionic compounds are a little bit soluble. So even silver chloride, silver bromide, and I think I've mentioned it before in the last unit, they're a little bit soluble. That's why we call them sparingly soluble. That's why they have a KSP value. They also have a delta H Sol value, meaning that somebody got this to happen. If there was no measured enthalpy of solution value, that means that nobody got that to dissolve. So if a compound has a measurable delta H Sol, no matter how positive it is, the fact that they got it to happen meant that there's value. So that means that it could be dissolved in water. Just enough effort. Yes.
Does the enthalpy of solution depend on the solvent?
Solvent, we're going to assume for everything here is water, but sure, solubility will change in different solvents. That's actually another concept that I've saved for later called KPC. I'm saving that for the organic part of the class because it's solubility in an organic versus an inorganic solvent. And also to bring back, you know, the Ks before the end of the year so that we review. Okay, so ion dipole bond. This is the next important thing you need to know. There is actually a non-zero chance that ion dipole bonds could have snuck their way into an AS chemistry paper. I've seen it happen, and I don't like when it happens because technically you don't learn about them until now. I believe I would have brought it up in passing in both pre-AS chemistry and AS chemistry, but technically these don't show up in the standard till now. So what is an ion dipole bond? It's actually the same as any other intermolecular force. You remember your intermolecular forces? Intermolecular forces. Do you remember IVIV? Which we call dispersion forces? IVIV. Do you remember they were weaker than? PD. And you remember those were weaker than? H bonds? Well, guess what? Right after that, something called ion dipole. So this is a little bit stronger than H bond. Can you surmise or can you guess why?
like
You've got the hydrogen bonding water, right? But instead of being connected to something partially positively charged, it's connected to something completely positively charged. the bigger the charge, the stronger the attraction. That's the general trend. Bigger charge, stronger attraction. So ion dipole bonds are bonds that take place between the metal ion or the non-metal anion and the water molecules when a solution forms. These little dashed lines means that it's an intermolecular force of attraction, not a covalent or an ionic bond itself. So this right here is the ion dipole bond. I want to focus your attention to how many waters are forming bonds with each ion. Is that more than one? Many, right? And that's where that word innocence. But I want you to focus the attention that it's many bonds that are formed. So it's not just one ion dipole bond, which is already stronger than hydrogen bonding. You're seeing several ion dipole bonds, which means that as these water molecules are surrounding these ions, a lot of energy is being released because this is bond formation equals energy released. Which means that this process of forming ion dipole bonds is always exothermic. Does that make sense? Because energy is always being released. So the ion dipole bond is the bond formed between an ion and a polar compound such as water. That's what we formally defined as an ion dipole bond. Sounds like dipole-dipole, but instead of having two partially positive, partially negatively charged things, you have something with a dipole, that's the water, right? And then the ion is the cation or the anion from your ionic compound, right? So that's why they call it ion dipole. We're not very creative here. You've got an ion and you've got something with a dipole, right? Forming a bond, yes.
Is it always 6 or could it be more?
It could be more, it could be less. It's usually not more for reasoning of spacing.
Or it could be 7 too.
I don't think so. Yes.
Does it depend on radius?
It can, yes, it's a factor. How many can fit around? Yes.
So if it's always exothermic, then why in like some of the what's it called? Why in the enthalpy of solubility is it sometimes endothermic?
Because this bond formation itself is not the enthalpy of solution. What you're gonna have to get to is the fact that two separate things are happening.
A hydration one.
Two separate things are happening. I'm gonna go back here. We're discussing right now these bonds that are forming, exothermic. What's the other thing that happens in forming a solution?
Oh, breaking bond.
These bonds have to break. So what's going to happen with the enthalpy of solution is a competition between how much energy it requires to break these bonds and how much energy is a result of forming these bonds. Does that make sense?
Okay.
So right now we're just talking about this part, forming these bonds. Yes, Caesar. I certainly hope I am.
Now I gotta check.
Now I gotta double check. Yes, I'm recording. Yes, you can scan through and go.
Okay, so that means if it's negative, like the ratio between like the bonds being formed is like it's more being there's like more
More
bonds
energy being
formed.
released than the amount that was required to break them. That's what that states. Good question. I told you it's a lesson to get through. There's a lot of factors here that come into play to be able to determine what that enthalpy of solution value actually is. And by the end of today's lesson, we got to get to those calculations. So notice it says here the energy released in forming the ion dipole bonds in order for something to be soluble would be enough to compensate for all the energy that's put in for the reaction to occur. And so either your delta H sol has to be negative or slightly positive. It can be slightly positive, like in the common example of sodium chloride. This energy released to form the ion dipole bonds is what we call enthalpy of hydration. So the enthalpy of hydration is when we form these ion dipole bonds, how much energy is released as a result of forming those ion dipole bonds. Yes.
So which one is this?
Energy released? It's always negative. Enthalpy of hydration is always negative. Yes. All right. And yeah, remember like that last Goldberg and the homework you have, because I looked ahead to your homework. You'll have that type of question where you have to check mark if it's always endothermic, always exothermic, or could be either. You're gonna have to do that for enthalpy of solution, enthalpy of hydration, and lattice enthalpy as well. All right, so here it is, enthalpy of hydration, the second important factor that we're looking at today. This is the enthalpy change, and yes, I believe they can ask you for this. The enthalpy change when 1 mole of a specified gaseous ion dissolves in, again, sufficient water to form a very dilute solution. And you may start questioning, gaseous ion? That's interesting. How can it end up being in the gas phase? Because you're starting, like if you go back to this process here, doesn't seem like we're entering the gas phase at any point. We are either in the solid or we're going to the aqueous phase. So the enthalpy of hydration is not something that can be directly measured, but is rather going to be a combination of experimentally determined lattice enthalpies, which use the gas phase, as we learned from lesson 1, and enthalpy of solutions, which we can determine in a lab. You can, that's why I said I'm leaning towards giving us a lab on this. You can determine an enthalpy of solution in a lab. That's something, you know, with your thermometer and your foam cup and you're dissolving, you can look at that energy change, the overall energy change. So that's one of the things that's confusing is you cannot directly find delta H hydration. You cannot. It is a combination of other, so you can only find it indirectly through other factors, the enthalpy of solution and the lattice enthalpy. But it is important, and that's because you can't actually do this, right? You're not actually going from a gas to an aqueous solution. Yes.
So it's enthalpy of hydration is lattice enthalpy and then solution.
Yes, that's going to be the combination. And I have a picture that makes it really easy to kind of put that together, but it's a combination of those two. So then you can see here, though, a calculation for an enthalpy of hydration for calcium. We know theoretically that if water surrounds the calcium ion, we're forming a lot of bonds. So that enthalpy should be negative. And notice that it is very largely negative. Very largely exothermic. And then I just circled that too. It's always exothermic. Could charge density affect the value of enthalpy of hydration?
Yes.
Meaning, if this wasn't calcium, if this was potassium, look, you got a computer. Why don't you look up what is the enthalpy of hydration? And they're going to give you a range of potassium. Because I don't know it off the top of my head. I'm good at chemistry, but not math. I'm not memorized all the delta H's.
-322 and -363.
Yeah, it's going to be a range because it depends on all the different various reactions and compounds that it could be combined with. So, and remember, it can't be directly found, so it can only be indirectly found. So you said -3 something?
Yeah.
So approximately -350 is what I think I heard, somewhere in that range. Okay. That's a lot smaller. Can we explain why? Smaller exothermic value. Why would less energy be released when water surrounds potassium than when water surrounds calcium? Isa.
Yeah, the calcium has a greater charge, so more molecules of water can form.
Correct. There's a stronger, here with a greater charge density, there's a stronger attraction. So greater charge density, stronger attraction to water molecules, which means that more energy will be released as a result of that bond forming. More energy released. That's the train of thought we have to have. So in this case for potassium, because there's a lower charge density, because the charge is +1 instead of +2, even though the sizes are about equivalent, they're close. They're isoelectronic, if you remember that word. Sizes are slightly different, but close to each other. The main factor here is the charge difference, and so we have a +1 charge versus a +2 charge. So could you guess that a +3 charge could be even more exothermic? Could be. If the sizes are close to equivalent. All right, continue. So now write equations for hydration. So what does this look like? Remember, this is gas to aqueous. Gas ion to aqueous. We have to use the gas ion, and I saw when I was watching the video this morning, the organic chemistry tutor explained it really well of why you have to use the gas ion, because if you were to put the equations together, the lattice enthalpy gas ions and the gas ions here will cancel to make your entire enthalpy of solution. So I do highly encourage you to watch that video that I posted as a resource. So the equations to represent the hydration of a sodium ion. Na plus, what's the initial phase? Gas. And now what? Add a bunch of water to it. So this stands for a bunch of water, a lot of water. And then this becomes Na plus H2. So this is basically saying isolated gas ion, throw some water all around it. Release lots of energy. That's the idea. Because this is only addressing bond forming. And hydration of chloride, Cl minus, plus lots of water, makes Cl minus in water. And so what they're not showing you is the actual drawing of the ion dipole bonds. I do have an exercise in here from the textbook where we draw the ion dipole bonds because I think it's a good exercise for us to practice just visualizing what that is. So let's continue. Here it is. Or notes about enthalpy of hydration. I added this last night. I pretty much just said this as a written note on the last slide, but I picked this up from the textbook last night as well. The value of enthalpy of hydration is more exothermic when our ions have the same charge, but a smaller ionic radius. Charge density, greater charge density. The value of delta H hydration is more exothermic if they have the same radii but a larger charge. We just saw that example. If they have a similar radii but a larger charge, again, charge density. And then over here, I also picked this up from the textbook. This is another image showing what's going on. In the whole process of forming a solution, you have to break these bonds. Then you form new bonds with water. And then you have this hydrated ions as your final result. So your ions are picked off of the ionic lattice and then dissolved into water. That whole process is the enthalpy of solution process. Welcome back. This right here is the delta H hydration. Is forming these bonds, right? These bonds that form is the enthalpy of hydration. What about breaking those bonds? What would that enthalpy change be? To break the bond in the ionic compound. It's the lattice energy. And it's actually, because remember, lattice energy is negative because it's forming bonds. So wouldn't it be the opposite of the lattice energy? Like the exact, instead of being negative, it would be a positive factor. So it would be the opposite of the lattice enthalpy. Kind of make sense? Because lattice enthalpy itself is putting the bonds together. Here we're addressing, well, how do we break them back apart? So it would be the same exact value that we know how to get for lattice enthalpy, but opposites.
Wait, so where's the solution in the H so?
Delta H sol is the final result of what happens when you put these two together. All right, so diagrams. Show 4 water molecules hydrating magnesium. What would we do? So draw diagrams. That means I want you to give me the Lewis structures with the dipoles. So start with the Mg. What charge would it have?
What?
Plus what? Yes, ma'am. Hi. There you go. Plus 2, right? Which part of water will be attracted to it? Oxygen or hydrogen?
No,
But maybe draw it on the side. Which part's negative, which part's positive? Out of all the water molecules, you should definitely know water, because we do a lot with water, right? That's water. So, which part of water would be facing magnesium? The oxygen. So face it like this. You should show it with its correct shape. What's its correct shape?
That.
Shapes will come back in Unit 4, just FYI, when we get to ligands.
Like, miss,
I said that.
miss, you know how like last year there were a bunch of like unused shapes? Are we gonna be doing those?
What's this?
Oh, like seesaw and T-shaped? No, we're
Oh,
not doing
then
that.
we're not backwards.
Oh.
Why did you say it like that? You knew what you were doing.
I know. That's the question. I know what they are.
For the hydration of aluminum,
Yes.
it's negative 4,665.
And that actually also communicates another thing. I believe, and you can double check me on it, that the charge is a greater factor than the size. The charge itself,
Oh, yeah,
like
I
B
think
plus
it
1
is.
plus 2 plus 3, is a much more significant factor than the size of the ion. That tends to be true. We learned that about initially. Melting points of ionic compounds, same thing, same idea. And then one more, right? So then,
It could have been 67, but
have I finished this though? Have I shown the ion dipole bonds? No. So how would I show those? Go ahead. For which one? That they tell you. You don't have to predict how many water molecules. It's just how you're just showing what it looks like. So this is the whole idea of hydration. Water molecules are surrounding the ion. You could be asked to do this for the positive ion, or you could be asked to do this for the negative ion. Not very commonly assessed, but as we like to say, non-zero chance. You could be asked to show with a diagram what's going on here. More commonly, they'll ask you to just write the equation. Most commonly, they'll ask you to make the cycle. Because that's what the standard says, right? Make the cycle. Continue? Yes. Questions?
You said ion dipole is like when the charge like completely positive and one's completely negative.
No, the ion's completely positive and the water is a dipole. So the one thing has a completely positive, completely negative charge, and the other thing is polar. Okay.
Wait.
So, quick review. Yes?
On like the Cambridge test, are they gonna have like another requirement for how many like molecules of water you need?
You do not have to memorize how many water molecules you need. Name the changes associated. First one. What's that called? So, this first one is delta H sol. Solid go in lots of water, make ionic compounds. That's the overall process of solution because you both need to break up the solid and then hydrate it. Those two processes are both happening in the enthalpy of solution. Second one, what's that?
Hydrating.
Delta H hydration. All the triangles, I apologize. What is C? Lattice enthalpy. Delta H lattice. You're forming the ionic compound from ionic gases. And the last one. This is another hydration. All right. So now that we've defined what in the world are these things even, enthalpy of solution, enthalpy of hydration, we can now see how they interact with each other. So I guess I reprinted this. I don't know if I recopied it. I probably did. Because I was messing around with it last night.
Imagine wasting paper.
It's one slide. All right. This is the meat and potatoes of this lesson right here. This is the enthalpy cycle that comes from the combination of the factors. And this is how it looks in what looks like a Born-Haber type cycle. So, take a look here. If I start with Na plus Cl minus solid, it would require energy to break that ionic solid apart. Do you agree? So you go to these high energy gaseous ions. Then it would release energy to hydrate them. The difference between how much energy it takes to break the bonds and how much energy to form the new bonds is what we call our enthalpy of solution. So I thought this image right here showed a really good idea of the difference in this process. The ionic solid here, the gaseous ions high energy, and then the hydrated ions lowest energy. Do you see it? Okay, this is another way, same type of diagram to look at it. And then this is how it goes into an enthalpy cycle. You have your gaseous ions. They go to ionic solid. We call that the lattice enthalpy. Your gaseous ions can also become ions in aqueous solution. We call that the enthalpy of hydration. So ionic solid, enthalpy of hydration. The enthalpy of solution is defined as the ionic solid going to the ions in aqueous solution. So looking at these arrows, we can come up with a formula. If you'll remember from enthalpy cycles, you have to follow the arrows. They go to the same spot. So whatever this is has to equal these two arrows. So basically, this right here, we can't determine this directly. So we use these two changes that we can determine, the lattice enthalpy and the solution, to come up with the hydration. Yes. Yes. For this one? I picked that up online somewhere. I picked that up online. The math will work. It'll be 1003 actually in what we had. This is a formula if you do not want to make the cycle. If you know that you are going to be unable to write out that full enthalpy cycle and you're just going to give up on those 2 marks if they happen to show up on paper 4. In order to solve the math, you still need this. You need to know that it is the combination of the lattice enthalpy and the enthalpy of solution that will give you the hydration enthalpies. And there are 2 hydration enthalpies, one for the cation, so one for the ion dipole forming with the water going around the cation, and one for the anion. So the way that I wrote out the formula is the enthalpy hydration for the cation and the enthalpy of hydration for the anion. Both of those combined. So it actually looks very similar to what we did with enthalpies of combustion last year, where you had to combust each part together. All right, so let's get some practice though. Can we try to draw an enthalpy cycle? Yes.
Can we go back for a break?
For which one?
Enthalpy of lattice. Is that the actual value of enthalpy lattice or is that the opposite one?
That's the actual value.
The one where we're going from gas to solid?
Yes. The way that I have it written here is just the actual values as is. You'll see later on when we combine the factors how we can look at it. But this is written just the numbers they give you. You can plug them in directly. Signs will be confusing. That's why I wanted to give you just the straight up formula. So if you're given in a Cambridge question, they'll never give you the opposite of the lattice enthalpy. They're just going to list out as a value. Here's the lattice enthalpy. It will always be negative. It will always be negative because that's what lattice enthalpy is. And then you can just plug this into the formula. Remember, if you were to move it to the other side to solve for Sol, it would switch from negative to positive. So that's what's going on here, is you're switching to solve for solution. All right, so draw an enthalpy cycle to calculate the enthalpy of hydration for magnesium ions. Let's get out our cycle. First thing I would do is fill my arrows in. This goes to this, and they both go down here. What was at the bottom? On the last slide, it says ions in aqueous solution. So for magnesium chloride, what would that be? MgCl2. What was up here? This is our gaseous ions. So this is Mg plus 2 Cl minus gas, GGs. This energy change from gaseous ions to solution, what is that called? From gas, not to solid,
Hydration.
from gas to dissolved in water. That's hydration. You have to trace what's going on. Yes.
On the bottom one, can you also can you just put Mg plus 2 at
Yes. Or Mg plus 2Aq plus 2Cl minus Aq. Both of these, there's no dot there. Those are the same thing. You can write either. What's the missing component here? Gas goes to solid, right? So MgCl2, solid. What's the name of that change? Gas ion to solid compound. Let's Enthalpy. This to this is lattice enthalpy. And talking about the sign, this to this is highly exothermic. Wouldn't you agree? So the sign, like from here to here, this is an exothermic process. You're going from high energy gas to solid. You follow that arrow, it's going to be exothermic. That's why I said the sign is the sign of delta H lattice in this formula. And then here from solid to aqueous, what's the name of that called? We take an ionic compound solid. We end up with the aqueous solution. That's the enthalpy of solution. And you'll see if you add the arrows, you come up with the same thing I gave you. The only difference between how it's written here and how I decided to write it on the first slide is notice I wrote delta H of hydration once because it is delta H of hydration, but technically there are two values, one for magnesium and one for chlorine. They're not the same as each other because one is a cation, one is an anion. They'll have different amounts of water possibly surrounding them. They have different charge densities. One's a cation, one's an anion. They have their own numbers. So you have multiple delta H hydrations here, one for each ion.
Think to find them.
Well, we're ready, aren't we? Here we go. Here's the math. So on a Cambridge exam, what they might do is they might ask you for the math and then they might suggest you have the ability to make an energy cycle if it helps you. So you can either use the formula that I do have written here, which you would have to memorize, right? Or you can choose to create the enthalpy cycle to come up with the same formula. I would just know the form. That's how my brain would work best. But you do whichever one works for you. Calculate the enthalpy of hydration for magnesium. So what do we plug in here? We have enthalpy of lattice enthalpy, right? So formula. What would I plug in for delta H lat? Negative 2592. Do I have delta H sol? I believe the sign is wrong here. Make this negative. Make this negative in your notes. I believe that sign is wrong. It's not positive 55. It is very soluble in water. I think I just forgot. I knew there was an equal, but minus 55. Because I'm telling you this is supposed to be minus. That's why. On the other side, delta H hydration cation, do I have that? Am I looking for that, right? So I would be looking for delta H hydration. And what about the anion? Negative 364 kilojoules per mole of chlorine. Does it matter that it's MgCl2? Did you think about it? I heard a grunt.
Of course.
Does it make sense that I would have to do 2 times negative 364 in this equation? Why? Because this is kilojoules for how many moles of chlorine? 1. How many are in your compound? 2. So just like the Born-Haber cycle, the amount must be considered. Yes. Okay, so the math here is actually not terrible. You just have to do negative 2592 minus 55, negative 2647. And then here, 2 times negative 364 minus 728. Move the 728 over to the other side. And that's negative 1919. Look, do me a favor, look up the enthalpy of hydration of magnesium. It'll be a range. Is that in the range?
And only one mark.
You find it? Enthalpy, hydration, magnesium.
Yeah, negative 1,500.
So definitely within the realm of yes. So does that mean you could check your answers? They're not going to be exactly the same because remember this is an indirectly referenced amount, but they should be close. So a lot of times when I'm working out questions, I will just check and be like, am I on the right track? Yes, I'm on the right track. I know that I've went through this thought process correctly. All right, so next slide. I know we're so very excited to see this.
Oh,
For 2 marks, can you come up with an enthalpy cycle? They moved the boxes around, which makes it even worse.
What?
incredible.
Of course.
Because they just had to make it even worse.
Okay, I like
And also for 2 marks, because
Even worse. So these 2 right here would be, this is how I approached it. These 2 right here would be my top boxes. Like this would be my left and this would be my right. That's how I went through it. So this, what?
That's just annoying. Like at that
This is
point,
my
it's just
gas
annoying.
ion. That's what I would do here. Gas ion, and then this would be my enthalpy of solution. Because what I'm doing here, just to give you my thought process, I took these boxes, I just went like that. Because I know this arrow is the one that they're pointing that way, and they move the boxes around, so I basically went like that. All right, so this is gas ions. This is ionic solid.
Wait, so the other 2,
And this, you have to fill them in how you want to do the arrows. That's part of the marks. Ionic solid, and this is my solution. All right, so we know gas ions go to ionic solid. Does solution go to ionic solid, or does ionic solid go to solution in this process?
Next solid dissolution.
So the arrow needs to point that way.
No, what, to add or out, I don't think.
You have to. You have to, actually. And then here, gas ions to solution or solution to gas ions in this process? Gas ions to solution, because that's hydration, right? So the arrows go this way. So now, this is gas ions to solution. What's that called? That's called hydration. So gas ions here are Al plus 3. And 3F minus. Do you agree? Gas ions to ionic solid. What's that called? Lat, right? What is this? Right? Ionic solid to solution. What do you get here? AlF3, AQ, or alternatively the ions in aqueous solutions. What is this called? Solution, right? And so what is our formula? Use this data in your energy cycle to calculate the delta H lattice. So it's the same formula, but the arrows tell you the story. It's lattice plus sol make the hydrations, right? Delta H lattice plus delta H sol is the enthalpy of hydration plus the enthalpy of hydration. Why do I write enthalpy of hydration twice? One for the cation, one for the anion. I'm calculating for enthalpy lattice. So, by the way, where are the 2 marks here? One is for all the correct boxes, what's in the boxes, and one is for the correct arrows.
Yay. All right.
And 1 mark now to do the math.
I mean, I guess that's whatever. It's easy. Yeah, I just need to get.
So delta H lattice, we're looking for that.
That's actually reasonable.
Delta H sol, do we have that? Minus 209. Aluminum, we have that. Minus 4,690. I think you looked that up earlier. Something like that. And then enthalpy of hydration fluorine, negative 506, but yes. Like that. Solve for delta H lat. Check to see if you got the same thing that I did. I already checked the mark scheme that I was correct, but negative 5,999 was the answer. That's what you get from this, and then moving the 209 over to the other side.
I got 466.
You got 46?
For aluminum.
Oh, okay.
Yeah.
It's the same. Again, it's not exact. It's a indirectly measured value. Continue.
I still think hybridization is more confusing than this.
You think which ones?
Hybridization.
Hybridization. However, that was in AS chemistry, and that, yes, I agree with you. That is another one of those weird. And by the way, they're both in unit 2.
Of course.
Hybridization is also in their unit 2. So, as I said, this for me is one of the more confusing topics of the year. But that's why I'm taking time to slowly, as much as possible, go over it.
If they move the box,
All right. So we've done the math. We've done the concept. And now we have that final thing that I mentioned at the beginning. We are going to now use this information to explain the trends of solubility of sulfates versus hydroxides. This explanation shows up, one of the 2, on, I would say, at least 75% of paper 4s. Does that mean it's common?
Of course.
These 2 lessons in a row have very common questions. Last lesson, the ion polarization, thermal stability, extremely common question. Here, this is another extremely common question, and it is a 4 marker, typically. 4 marks, typically. Yes.
Is it possible that they're like a definition question will show up 2 times in this, like the same test? Like it does.
Different definitions, not the same. Not the same definition in 2 different places. And it's interesting, the paper 4, more than the paper 2, the paper 4, there's usually a question for each unit. So you'll see a question that's all about unit 1, like they'll give you Ka, KSP, all that stuff. There'll be a question on unit 2, which will be like your Born-Haber cycle, your thermal stabilities, and then your entropies, which are coming up. And then it'll keep going like that. So the paper 4, whereas in paper 2, you don't know, you can study all these things, and the things you decide to study don't show up on the test. In this class, you can be guaranteed that every unit's going to show up on the paper because it's a larger paper. So it's going to be there in some way. All right, so what is the trend? We know that the trend is that the solubility decreases. This is measurable. Magnesium sulfate has a solubility of 1.83 moles decimeter cubed. Barium sulfate has a solubility of 9.43 times 10 to the negative 6. Would you agree that this is much smaller?
Yes.
Much smaller solubility, meaning a lot less involved. And so we know experimentally that that's true. And so now what Cambridge is asking you to explain to them is why. Why is this true? And they want you to use the concepts I just taught you to figure this out. So let's take a look. And I broke it into the different factors, and then we're going to take a look at the overall equation. So looking at sulfates, as I go down the group of the periodic table, how does the hydration enthalpy change? Down the group. As I go down the group, what should I notice about the hydration enthalpy? From magnesium to barium. This is a larger ion. So the charge density decreases, which means less energy released. That's what we learned earlier in today's lesson, right? And so this last part is important. This decrease is relatively large down the group, meaning that the decrease in energy released is significant and depends entirely on this increase in the charge density and not at all on the other ion, the sulfate, because the sulfate is not changing down the group. We're comparing MgSO4 to CaSO4 to SrSO4 to BaSO4. So when we talk about hydration enthalpy, this isn't changing, right? The hydration enthalpy of sulfate is not changing. Only the hydration enthalpy of the cation is changing. That's what this statement says. Sort of makes sense so far? So that's factor one. Factor one. Factor two is the change in lattice enthalpy down the group, because it's the combination of the hydration enthalpy and the lattice enthalpy that gives us the enthalpy of solution, right? So the change in lattice energy down the group. The lattice energy will be greater, and what we mean by that is more exothermic. Release more energy. Lattice energy is greater if the ions forming the lattice are small, meaning a larger charge density. Greater charge density. Lattice energy decreases down the group. Again, just like hydration enthalpy, right? Because as we go down the group, your ions actually get larger, which means the charge density decreases, which means less attraction. And this is the factor that you've got to get to. In comparing the size of your cation and the size of sulfate in each of these scenarios, what they're saying is that sulfate is very large in comparison to a single metal ion. So sulfate is very large. So this means that the sulfate ion contributes a greater part to the lattice enthalpy than the cation does. When they come together, this is the more important contributing factor. And so this decrease in lattice energy becomes smaller down the group. And so the factor of lattice enthalpy is more important than the factor of the enthalpy of hydration as I go down the group. Because the sulfate ion is very large in comparison to the metal ion. So whatever's happening with the lattice enthalpy of the sulfate is the more important commanding factor here. So then this is the way that you have to explain it. Both the lattice enthalpy and the hydration enthalpy get smaller or become less exothermic down group 2. But the hydration enthalpy will change more in sulfates. So the lattice energy of the sulfates decrease by relatively small values down the group. And this is because the sulfate is a large ion. So the difference in the size of the cation is not as relevant as a factor for the lattice enthalpy of them coming together. The enthalpy of hydration, however, where they're split apart and the water molecules are surrounding them, this changes by a greater factor. So the enthalpy change of hydration gets less exothermic by a greater factor. And so what happens is, as I go down the group, the enthalpy of solution becomes more endothermic. And if it becomes more endothermic as a result, this means that it's not going to dissolve as well. And so the solubility of the group 2 sulfates decreases. So I understand this is extremely confusing. To me, it's confusing. And I've been studying chemistry for a long time. So the way that I like to reason it is I think about the formula itself, like what's happening. And so we say that both of these are decreasing, right? So what is the sign of delta H hydration? Positive or negative? This is what I was saying, Daniel. This is negative. What is the sign of delta H lattice itself? Negative. So you have a minus, a minus sign.
So
So technically, if we carry this through, the delta H sol is actually a combination of this factor being negative and the delta H lattice being what sign? Positive. Because it's a subtraction multiplied by a negative sign. So this would actually be a positive factor. So these are two competing factors that result in your enthalpy of solution. And so this is what's happening. If my hydration enthalpy decreases more, what does that mean? What is decreasing? A negative value. And what does that mean? Thinking about number lines. If it's decreasing more, it's getting closer to a negative decreasing more is getting closer to 0. Would you agree? So a smaller negative. That's the same thing as saying less exothermic, which is how you have to describe your answer, right? So if this is a smaller negative and this changes more, and this is a positive value, right? As I go down the group, we get a smaller negative value. This positive factor is still there. Would the solution be more likely to be negative or positive? It's positive. And that's why they're saying, remember, delta H sol, positive means less dissolves. That's the idea. Using the signs. If your brain is like mine and sees a bunch of negatives, and you can just write on a flashcard the things you need to say and just memorize it, or come up with a cute little acronym that helps you. Both of the lattice enthalpy and the hydration enthalpy change. Which one changes more? It is the hydration enthalpy that changes more because the sulfate ion is so big. The lattice enthalpy does not change as much for those ions to form. And then because this is the dominant factor, this is getting smaller negative, that positive remains, solution is positive. Meaning as I go down, less soluble. Told you. 4 marks. Okay, so here, I apologize again. The explanation for hydroxides is also 4 marks.
Oh.
And is exactly the opposite of the explanation of sulfates. Why?
That's awesome. That's wonderful.
The literal only difference between hydroxides and sulfates is what? What do you think? The anion. Sulfate was large in comparison. What is hydroxide? Small. So let's talk about sulfate versus hydroxide real quick. Sulfate is this. This is sulfate. That's its actual with its correct resonance structure. If you don't know what resonance is, if you're studying for the Olympiad, that's something we'll go over. Don't stress it if not, because resonance isn't taught by Cambridge for some reason. But this is the correct, so this is what sulfate is. And then what is hydroxide? OH with a minus charge. Would you agree that this is larger and this is smaller?
Yeah.
Larger, smaller. So here, because the hydroxide is smaller, the cation becomes a greater factor in the lattice enthalpy. So therefore, in this scenario, the lattice enthalpy changes more when the size of the hydroxide, because the size of the hydroxide is smaller, the opposite is true. The lattice enthalpy decreases more than the hydration enthalpy. And so if the lattice enthalpy decreases more, the opposite factor, when I'm looking at the formula, the opposite factor is decreasing more. So I'm getting a smaller positive, but the negative remains closer to the same. So a smaller positive, greater negative means more negative means more likely the solution will dissolve. Yep. And that's the explanation for hydroxides. I told you it was gross. So before we go, let's try this out as a practice Cambridge question. I told you it's 4. So how do you need to frame your answer is, what I wanted to address before we leave today.
4 max out of the 100.
The enthalpy change of hydration for sodium is -410. Suggest an explanation for why hydration of the sodium ion is less exothermic than Mg2+. So this is not what we just learned. This is what we learned earlier today. Why is Na+ less exothermic, Alexander?
Would that be because sodium has a smaller radius?
It's the charge factor that's important here. But you should say charge density. So the way to explain the answer best is Mg2+ has a greater charge density. So that would be 1 mark. What does that mean? Is the second mark. Greater charge density, what does that mean? Which means that water would be more attracted to it. It would release more energy. Sodium would release less energy. Which means water will be more attracted to Mg2+ ions than Na+ ions. So you have to get the comparison in there. Like what you're comparing, which one's a greater or a smaller charge density. So that's the second mark, is talking about the attraction between water and the ions. And the final one is describe and explain how the solubility of the group 2 sulfates varies down the group. What are the 4 marks? Describe means you can pick up a mark if you can just tell us what happens. What happens?
All right,
Sulfates, do they increase or decrease? Sulfates decrease in solubility down the group. Okay. That's mark 1. Where's the other 3? That's where you have to now compare your hydration enthalpies and your lattice enthalpies. So how do they want you to frame the answer? Both lattice enthalpy and hydration enthalpy decrease. But which one decreases more? Mark 3. Which one decreases more? In this one, it is hydration enthalpy decreases more. That's why I said they're going to be opposite. You're going to get confused between sulfates and hydroxide. You've got to study it. Write it down. Get a flashcard if you need to. It does have to do with the size difference. And so what this ends up being, the final part, is delta H sol becomes less exothermic. Or you could say more endothermic. Which basically just tells us that it's not going to dissolve as well, is the idea. I will be putting on your exam either describe and explain for the solubility of sulfates or hydroxide, because it is a common question. And I will also put a question on the thermal stabilities from the last lesson. So it is something that you need to rehearse. But congratulations, you got through what I think is the most complicated lesson of